Good afternoon, students. Let's begin today's session. So,
Good afternoon.
good afternoon. We were looking at the details about rolling motion without slipping yesterday. Let's continue from that point onwards. Okay, so we had seen the concept of rolling without slipping as basically a constraint relation that the combination of rotation and translation for a round object like a sphere or a cylinder moving on a plane surface or moving on any surface for that matter. The combination of rotation and translation should be happening in such a way that the point of contact should be at rest. Or the point of contact should not be slipping. So if this is the center of mass and this is the point of contact, we had seen that the no slipping condition or what we call rolling without slipping is that the point of contact in this case the point level P should be at instantaneous rest. That means the velocity of that point of contact should be zero, which of course means that if the center of mass is, for example, moving in this direction with VCM, the angular velocity about the center of mass must be such that the net velocity of this point comes out to be like the velocity of the center of mass minus r into omega, where r is the radius, and that should be zero. So the condition that we get for rolling is that VCM and omega should be related to each other such that VCM should be equal to r omega. And this is what creates that condition that the point of contact is at instantaneous rest. So this is what we call the rolling constraint or the constraint relation for rolling without slipping. And to that end, we had seen one example yesterday of applying a force on a cylindrical object. I think it was the force acting through the center of mass horizontally.
Sir, can you send that extended PDF?
Yes, I will send the recording and the PDF in some time today. Okay. So
after this lecture.
Yeah, sorry.
Sir, after this lecture.
Yeah, I'll send. Okay. So now today, so this is a repetition of what we've seen yesterday. It's a recap. Now today, let's begin the lecture by understanding the situation of rolling happening down an inclined plane. So let's say we have a rough inclined plane. So the friction on its surface will prevent slipping at the point of contact. And this angle is theta. And now we've got, let's say, a solid cylinder which is released from rest at this position. So this is a solid cylinder of mass m and radius r. And this is a rough surface. So the cylinder is gently placed on the surface and released from rest. So since the surface is rough, assuming sufficient friction is available to prevent slipping, the cylinder will roll down. The moment it is released. So we want to find the acceleration of the center of mass and the angular acceleration about the center of mass in this situation. Okay, so once again, what we will do is we'll start by understanding the free body diagram of this cylinder. Now let's say this is the inclined surface. So at this point of contact, this is the normal to the incline and this is the parallel to the incline at the center of curvature. So you realize that the forces acting on the body are obviously not the weight which acts vertically down through the center of mass. Mg acts as if it's acting through the center of mass. Then there's this normal contact force which acts at the point of contact in the normal direction. And you can see that now the combination of these two forces, it gives it a tendency to slip down the incline. Suppose this was a frictionless surface, then it would be slipping down the incline. Okay, so to prevent that tendency for slipping, what happens is now friction acts at the point of contact, and it acts in such a way that it acts opposite to the slipping. So friction acts like this. So this is the friction that acts. So when we look at the free body diagram, what we understand is that mg sine theta, okay, gives the cylinder a tendency to slip down the incline. So therefore, at the point of contact, P, friction acts up the incline to prevent slipping. And obviously the cylinder starts rolling down without slipping. So next thing, we will take the components and all that, and we'll write the force and torque equation. And from that, we will understand how to calculate the acceleration of the center of mass and the angular acceleration about the center of mass, both these things. Okay. So we can start by just noting down this situation. We'll discuss further. Okay, so let's now solve the free body diagram.
Sir, I was writing.
Which I haven't finished writing. Okay. Okay, done with this now. Okay, so now after resolving the forces, a free body diagram will look
Sir,
like this.
the equations will be same now, that ACM equal to R alpha and then mg sin theta minus f equal to mac.
Very good, that's correct. Okay, so constraint relation will be what you said, that A is equal to R alpha. And then you resolve mg, so there is mg sin theta minus friction acting down the inclined plane. So this is our mg sin component. Mg is cos component. Then friction is acting at the point of contact like this. So have you written the torque equation also?
Yes, the torque equation.
Okay, very good. So normal reaction is acting like this, and the center of mass will have a linear acceleration like this, and about the center of mass there will be an angular acceleration. So over a period of time, the linear velocity of the center of mass will be equal to acceleration into time, and the angular velocity will be equal to alpha into time. So VCM equal to R omega here implies again that acceleration of the center of mass is equal to R alpha. So this is the no slipping constraint relation. So always in rolling motion, we start with the constraint relation. Then you can, second thing you can write is your net force is equal to mass into acceleration. Newton's second law application. So here along the inclined plane, we will have mg sin theta minus friction is equal to mass into acceleration. So that's our second equation. We also have the equation that normal reaction balance is mg cos theta, but that's not going to be important for us here. Okay, and then we have torque is equal to net torque is equal to I alpha. So here the torque is provided only by friction, as you can see. So that should be equal to mr square by 2 alpha. And you can see the sense of the torque is anti-clockwise. So the sense of alpha will also be anti-clockwise. So this torque equation, this becomes my third equation. So just like yesterday's problem, we have three equations and three variables. Acceleration of the center of mass, alpha, and friction. Of course, friction should be less than equal to mu n. But apart from that, friction is not a fixed value because here friction is acting at a point which is stationary. So friction here acts at a point which is at rest with respect to the ground. Okay. That is the no slipping condition. So friction is not kinetic friction. In fact, it is a special type of friction. It is called rolling friction. And rolling friction is similar to static friction, such that its magnitude is less than equal to coefficient of static friction into normal reaction. This is just an additional point about this. Okay. Now the method of solving will be the same that we discussed yesterday, that you always start with the torque equation and first divide both sides by r, okay, and substitute alpha as E by r. So when you divide both sides by r, you're getting friction is equal to mr by 2 because I've divided by r, and then I'm substituting alpha as ACM by r. So here the friction is just like yesterday's problem, it's becoming MACM by 2. Now substitute this in equation 2. So we have mg sine theta minus friction, which is half of MACM, will be equal to MACM on the other side. So from that we will get the acceleration of the center of mass. When you calculate it, it will come out to be 2 by 3 g sine theta. Just verify my answer, all of you. Okay. And therefore alpha will be just this thing divided by r.
Hold on.
Okay, now because rolling down inclined plane is a very
Sir,
important
can you
special case of
once
rolling.
explain that friction, rolling friction?
Yeah, rolling friction, as I've written down over here, it is a type of friction which is similar to static friction, unlike kinetic friction, because it acts at a point where there is no slipping involved. So its value is not equal to mu n. It can be less than mu n also. And which mu is going to be important in calculating the limiting value of rolling friction. It is the coefficient of static friction, because ultimately that point is static with respect to the surface. You understanding the point? The body is not static, but the point of contact is static.
Yes,
Because
sir.
it's not slipping. So it has a similar behavior to static friction rather than kinetic friction. In fact, we'll be discussing more about this. Okay. But before that, we'll also see here that alpha was ACM by R. So in this case, alpha will become 2 by 3 G sine theta divided by R. And the amount of friction that we saw was MACM by 2. So that means the amount of friction that is going to act is going to be mg sine theta divided by 3. So this value that we are getting, this is the magnitude of rolling friction required. So that it's able for the cylinder to be able to roll without slipping. So that also tells us that since the maximum rolling friction available to us is going to be equal to mu n, okay, this is the limiting friction. So here the condition becomes that the actual amount of friction acting should not exceed mu n. So actual amount of friction required for rolling condition is mg sine theta by 3. It should be less than equal to mu into n, which was mg cos theta. So that shows us that there is a minimum value of friction coefficient required. If you just invert this relation, you can see that tan theta by 3 is less than equal to mu, or in other words, mu should be greater than equal to 1/3 of tan theta, whatever that angle of inclination is. That means a minimum mu of tan theta by 3 is needed for rolling. If the coefficient of friction is less than tan theta by 3, okay, if mu is less than this value, then the cylinder will slip. Okay, it will not be able to roll without slipping. So now further analysis of the problem, this also becomes important, that we have solved earlier for the acceleration of the center of mass, assuming that there is enough friction to prevent slipping. But that much friction should actually be available. No? And how much friction is available depends on the coefficient of friction and the angle of inclination. Because normal reaction is mg cos theta. So the larger the angle of inclination, the lesser the normal reaction available to us. And it also depends on the coefficient of friction. The larger the coefficient of friction, the more the normal reaction, the more the limiting friction available to us. So ultimately, whether or not this friction is there, enough friction is there to be able to make the object roll without it slipping at the point of contact, that depends on a certain condition. And that condition here is that mu should be greater than equal to tan theta by 3, or at least this much of coefficient of friction, tan theta by 3 should be there. So for example, if theta was 37 degrees, so tan theta is 3 by 4. So you can see mu should be greater than equal to 1 by 4. So at least 0.25 should be the coefficient of friction. If it's more than that, then also it's fine. But if the coefficient of friction is less than 0.25, then the cylinder will not be able to roll without slipping. It will be coming down in such a way that it's slipping. So in that situation, how to calculate A and alpha and all, we'll discuss that. But first, write down this condition. So we have done this for this particular problem where we have a solid cylinder rolling down the inclined plane. We will also generalize this result for any object rolling down an inclined plane, whether it is a solid cylinder, a solid sphere, or a hollow shell, or whatever. and we will discuss those general equations because there's a very common type of question in JEE. But first, just make sure you understand this limiting condition on friction. Okay, now let's understand the general case of rolling down an inclined plane. Same type of diagram, but if we have, instead of a solid cylinder, it could be any round object. The formula of moment of inertia may not be 1 by 2 mr square, it could be any factor into. So here, if the mass is m, radius is r, and the moment of inertia about the center of mass is some factor beta into mr square. Okay, where beta is a dimensionless factor. Beta is numerical constant. So for example, beta is equal to half for a solid cylinder. Okay, beta is equal to 2 by 5 for a solid sphere.
Sir, it is only in rolling case, no?
Yes, we are discussing this general case of rolling down an inclined plane. Okay. Then its free body diagram again will be the same as the one we discussed previously. Only the value of I, instead of half mr square, we will replace it with beta times mr square. So the component of its weight down the inclined plane, which is giving it a tendency to slip. Just a moment, people. I'll stop it. Reshare that file. Yeah, so coming back to this free body diagram. So you have mg cos theta and mg sin theta, the two components of weight, which will be like this. And normal reaction acting like this through the center of mass, and finally friction acting at the point of contact. So same free body diagram. Only difference is that the value of moment of inertia we'll just replace as a general value, that it is beta times mr square. So you get general formulae for all these things, like the acceleration of the center of mass. I'm just showing it as a vector on top, and the angular acceleration about the center of mass. So you have ACM is equal to R alpha. That's our first equation, which is the no slipping constraint, because we are assuming that it's rolling. Then we have mg sin theta minus friction is equal to mass into acceleration of center of mass. This is the net force equation. And friction into radius is equal to I alpha. This is a torque equation. You can see it's again an anti-clockwise torque. So solving these three equations by the same method now. So the third equation, beta times mr square into ACM by R. So this will give us that the friction is beta times MACM. So now substitute this in the second equation. So we get mg sine theta minus beta times MACM is equal to MACM. So this gives us the general equation that acceleration of any body rolling down an inclined plane is given by the formula g sine theta divided by 1 plus beta. And now so you can use this as a direct formula. An objective question and all, you want to find the acceleration of an object rolling down an inclined plane, you can use this as a direct formula, and you have to just substitute the value of beta according to what
Yes.
kind of object it is, whether it is a hollow sphere or a solid sphere, etc. So that's the first thing. Accordingly, alpha will be equal to ACM by R. So G sine theta upon R into this factor of 1 plus beta. And most importantly, next we will discuss about the limiting friction condition also. Okay. That's why this generalization becomes important, so that you have a method of just uh, checking for the limiting friction given a numerical problem.
Sure, done.
Okay, so understood this. Now the limiting friction condition we'll understand. So from the third equation again, we have that friction is equal to beta times MACM. So now substituting this value here, this becomes like this: beta upon 1 plus beta into mg sine theta. So this is the magnitude of friction needed for rolling to occur. And as I told you, generally when we talk about rolling, we mean rolling without slipping or rolling in the no slipping condition. But the available friction, it has a limit that it should not exceed mu n. Okay, so beta upon 1 plus beta into mg sine theta should not exceed mu into mg cos theta. So that when you invert this relation, it gives you the condition on mu, that mu should be greater than equal to beta upon 1 plus beta into tan theta. So this is the limiting condition on coefficient of friction mu for rolling to occur, rolling without slipping. Okay. So this formula also becomes equally important to remember. Apart from the acceleration of the center of mass, this formula that the minimum coefficient of friction we require is this value, beta upon 1 plus beta into tan theta. And you can see that for the previous problem, the value of beta was 1/2. So when you substitute a limiting condition. Okay, so we will see in a couple of numerical problems next how this becomes important.
Sir, done.
Okay, so next up, let's look at a specific numerical problem. So next example.
Our theory is over now.
For this rolling inclined plane, yes.
Rotational
Yeah, mostly is done. Just we have to discuss about kinetic energy and work energy application in rolling situation, but basically it's done. Okay. So in the next example, we will see this situation. There is an inclined plane. So an inclined surface at theta equal to 45 degrees has a coefficient of friction equal to 0.32. So you have to find the acceleration of the center of mass and angular acceleration and friction acting on, first part, a solid sphere of mass 5 kg and this thing radius equal to 20 centimeter. And the second case, a hollow spherical shell, same mass and same radius. In each case, determine if the sphere is rolling without slipping or slips as it rolls down. So through this question, you will understand how to use this theorem properly. Just make a note of the data and start working on the question.
Like, could you please scroll up?
Sorry? Yeah, you've not written on this part?
No, sir, that part I did. So now could you just show the question?
Okay.
Sir, that what is last line written?
What is?
Last line.
Or it slips as it rolls down.
Sir, means
You should understand, we've been discussing rolling with slipping versus rolling without slipping since yesterday. If it is slipping, that means the point of contact is not at rest. Okay.
Sir, G 9.8 or 10.
Okay, so let's understand. So here for the solid sphere, moment of inertia is 2 by 5 mr square. So beta's value is 2 by 5. So first of all, for no slipping condition, mu should be greater than equal to beta upon 1 plus beta into tan theta. So mu should be greater than equal to 2 by 5 upon 1 plus 2 by 5 into tan 45 degrees. Okay. So mu should be greater than equal to 2 by 7 into 1. So mu should be greater than equal to basically nearly 0.29. Okay. Whereas what is the value of mu given to us? 0.32. Okay. So actual value of mu is 0.32. So this condition is getting satisfied. So that means the solid sphere will roll without slipping. So the solid sphere rolls without slipping with an acceleration
5.0.
yes 10 into 1 by root 2 divided by 1 plus 2 by 5. So 5 by 7 into 5 root 2. Okay. Now root 2 we can take as approximately 1.4. So 25 into 0.2. So nearly 5 meters per second square. The acceleration of the center of mass. And the friction acting on it will be
10 point. We can do direct formula, no? ACM.
it will be equal to mass was I think how much 2 kgs, right?
5 kg.
5.
5 kgs. So nearly 14 newtons of friction will be acting on it, whereas the maximum friction available would be more than that. It would be
Sir, which formula used for finding friction?
which formula is it for?
Finding friction, sir, you have given that
The formula
beta
we
upon 1
discussed
plus
earlier.
beta. No?
In the general case, see how we no, that is for the coefficient of friction. This is for the value of friction itself.
Can you once scroll up then?
You have not written that part down.
Sir, I have written, but I want to check.
Just a minute. Okay.
So you have written a beta upon 1 plus beta mg. Or we can use directly also na beta into m into ACM.
Yeah. Yeah, I mean the formula is actually that it's beta into m. So in this case, it is 2 by 5 into 5 kgs into the acceleration, which is 5. So the friction required is nearly
10.
10 newtons approximately. Whereas the available friction is more than that. It's 8 root 2. So that's about 8 into 1.4. So you can see that our condition is okay. The required friction is less than the limiting friction. It's fine. So rolling will take place. Okay, so that's how analysis of this kind of question can become very fast because you know that formula from beforehand. Okay. Now, whereas in the second case, if you check again, you will find that this might not be happening. So then you have to think a little carefully that if rolling without slipping is not happening, then how we will calculate ACM and alpha? Because the rolling constraint will not hold. A will not be equal to R alpha because it's slipping then. Okay. So while others might be noting this down, those of you who have completed this, just try to work out the second part. So first of all, figure out that in the second part whether or not rolling is happening. I mean, rolling without slipping is happening.
Sir, so for rolling, can we check only that mu value?
Can we take only?
Check only that mu value.
I didn't understand you. For which case?
Sir,
Ah,
sir,
tell me.
for rolling, can we check only for that mu value?
Yeah, that's what you need to do. No? You need to check
So no,
whether
you
you
have
have
find
enough
that limiting friction
you
also.
need to
That
check if enough friction is available. And if it is available, then you can use the formula directly for ACM. It is G sine theta upon 1 plus beta. But what I'm saying is if that condition is not satisfied, then how you will find the ACM. So that you need to think little carefully. Okay.
yes.
So people, let's figure out this second part. So obviously, all of you must have understood that it does slip. It's not the case of no slipping. So if it slips, then we have to figure out what kind of friction acts and how to calculate the ACM and the alpha. So it's not that because it's slipping, friction will not act. Friction is
So
going to
we
act.
will use the maximum value of friction.
Sorry?
Sir, we will use maximum value of friction in force net is
Yes.
equal to mass.
Yes, because which type of friction will act now? Kinetic friction will act. So we can already see that when we check the value for no slipping condition, we saw that mu should be greater than equal to beta upon 1 plus beta into tan theta. Now here it's a hollow sphere. So hollow sphere has beta's value how much? 2/3. So here mu should be greater than equal to 2/5 into tan 45. When you calculate this thing, it will come out to be like this. So mu should be greater than equal to 0.4, whereas given the value of mu is 0.32. So you can see that this condition is not getting satisfied. So therefore, the shell will slip. So if it is slipping, then that means at the point of contact P over here, at the point P, there is slipping down the inclined plane. Okay, because there isn't enough friction. So mg sin theta is dominating. So what will happen? Kinetic friction will act. Kinetic friction whose value will be equal to, in this case, mu n, but otherwise in general it should be mu k into n if there are separate values given, but here there's only one value given. So kinetic friction acts and ACM is not equal to R alpha. In fact, ACM is greater than R alpha, so that at any point of time VCM is greater than R omega. So the velocity of the point of contact is not zero, it is downwards. So it's slipping. Okay. So now keeping that in mind, now our free body diagram is actually the same, but only the thing is the type of friction acting. Instead of it being,
Sir, kinetic friction is greater than equal to mu n, no, but
no, kinetic friction is equal to mu k into n beta. Kinetic friction never has a, no, it's equal to the limiting value, no? Static friction is the one that can be less than the limiting value, and therefore also rolling friction. Understood the point, no?
yes.
Okay. So this friction that is acting now at this point of contact, this is now kinetic friction. So it is mu into n. So it's still going to be spinning. It's going to have an alpha, but that alpha will not be enough to prevent slipping, because ACM will be greater than R alpha. So the point of contact will be slipping forward. Okay. So for this FBD now we'll have the force equation that mg sin theta minus kinetic friction is equal to MACM. Normal reaction is obviously equal to mg cos theta, and we have kinetic friction into R is equal to ICM into alpha. Okay. And no third equation is required because this kinetic friction is a known quantity. Kinetic friction is mu mg cos theta. Okay. So from the first equation, we'll get the acceleration of the center of mass like a sliding body's acceleration, which you've seen in friction before. G sin theta minus mu cos theta. So यहाँ पे how much it will become? It will become 10 into 1 by root 2 minus 0.32 upon root 2. So the acceleration of the center of mass is 10 by root 2 into 1 minus 0.32. So that's 0.68 into 5 root 2. So the linear acceleration of the center of mass will be, we'll calculate the value. Okay. And similarly from the second equation, the torque equation, we will get the value of alpha. And we can verify later that ACM will be greater than R alpha, okay, which means that it will be having slipping as it goes down. Okay. So just if you haven't worked this part out till this point, just work it out here. Then we'll come to the calculation of alpha also. There isn't sufficient friction available to prevent slipping. So let's calculate that value first. 5 root 2 into 0.68. That's about it. And from the second equation, now we can calculate the alpha. So when we calculate this, this comes out to be about 3.39 divided by R. So we can see that the alpha's value is such that if you compare it with the ACM's value, you can see that R alpha is nearly 3.4, but ACM is 4.76. So ACM is greater than R alpha. Slipping is occurring as expected. Friction is not able to cut down the value of ACM and give it sufficient spin so that the point of contact is not slipping. Because in the first case, that was what was happening.
Sir,
Yes,
sir, but when the body will slip, how it will rotate?
because friction is acting. No, beta.
Okay.
Friction is not able to make it rotate enough, but it's still making it rotate. You understand? No?
Okay.
If we had a larger value of mu, then alpha would have been larger than this and A would have been less. So A would have been equal to R alpha. But nonetheless, it is slipping the point of contact. So friction will keep acting. And as long as friction acts, there is torque acting on the body, you can see. So friction is creating torque. So it keeps spinning, but it's just that it doesn't spin as much as is required for the rolling condition to be satisfied.
Okay. That means it is spinning, but it is very less.
Yes, it's lesser than what is required. So this kind of motion is called rolling with slipping. Whereas when there's no slipping at the point of contact, we say it is perfect rolling or rolling without slipping. Okay, so hope this question is fully clear.
1 minute, sir.
Okay.
Done.
Okay. Now, next thing we'll discuss about friction in general, and also you can see in this type of question it's happening that when a body is rolling without slipping, okay, while friction, and that type of friction is then called rolling friction, acts at the point of contact, then the work done by friction is zero. That is, rolling friction is zero. The reason for that is that power developed by a force, is F dot V. So when rolling without slipping, okay, the point of contact's velocity is zero. So therefore, the power delivered by friction, which will be the amount of friction acting at the point dot product with the velocity of that point, this is zero. So the power is zero. That means rate of work done equals to zero. Okay. So that means friction is zero. Whereas on the other hand, if there is slipping occurring, then of course the friction acting is kinetic friction, and there will be this thing. There will be negative work done by it. Case of slipping at the point of contact, the friction acting, it is kinetic friction, and the work done by kinetic friction is not zero, it is a negative quantity. So in that case, kinetic friction does negative work on the object. Okay. But in the case of rolling without slipping, if friction is acting, like in the case of rolling down the inclined plane, it will not be doing any work.
Sir, done.
Okay, so now another way of understanding.
Sir, I was writing.
Sorry.
Sir, I was writing.
Okay. Okay, done.
Yes, sir.
Now, for example, we can see the application of this concept that rolling friction does not do work in a situation like this. Suppose we have an inclined plane whose total length from the top to bottom here is, let's say, 20 meters. This angle of inclination is 37 degrees, and let's say a solid cylinder is released from rest. So released from rest at time t equal to 0. So after some time it reaches here, and by now it has some linear speed and some angular speed. So we want to, so the solid cylinder released from the top of the inclined plane. Now here we'll assume that it's it's a rough inclined plane. Okay. Rolls down without slipping. So it's in that perfect rolling condition. So we have to find its VCM and omega at the bottom. Okay. So the solid cylinder, let's say, has some mass that is given to us, some radius that is given to us. Take G as 10 meters per second square. Coefficient of friction mu is not given, but it's just assumed that it's enough to prevent slipping. Okay. So we have two options here. One option is use the standard rolling equations. To find ACM, alpha, and all these things, and then use kinematics to find VCM and omega. So let's go with that method first. So we use the standard formula. Our ACM is how much? It is G sine theta upon 1 plus beta. So in this case, it is 10 sine 37 degrees divided by 1 plus half. So it is 10 into 3 by 5 divided by 3 by 2. So it is 6 divided by 3 by 2. That's how much? 4 meters per second square. So this is the acceleration of the center of mass. Okay. Now use kinematics that it's starting from rest with the given acceleration. So by the time it reaches this kind of displacement, the displacement is equal to L. So V square is equal to U square plus 2AS, this formula. So our V square will be equal to 0 plus 2 into 4 into that displacement is that length, which is 20 meters. Okay. So how much
Sir,
will
we
V become
can
according
find that VCM by R omega also, no?
नहीं ACM R omega से कैसे निकालेंगे बेटा?
Sir, VCM.
VCM. So how from R omega, tell me? For that we'll need to calculate omega first, no?
Oh,
It's the other
yes.
way around. No? We'll find VCM from this, and from that we'll find R omega. You're getting my
Yes,
point?
yes.
Okay. So it's square root of how much now? 160, isn't it? So 4 root 10 meters per second. So this will be V. So omega will be equal to V by R. Okay. So 4 root 10 divided by the radius, which I think was, what was the radius? 5 centimeters. So 4 by, so this much in radians per second. So this is one method of doing the problem. Okay. However, we can also skip all this and we can do it by the second method, which is work energy. So just make a note of this first, then we'll come to the work energy method.
Sir, done.
Okay, now let's come to the work energy approach. So in the work energy approach, what we'll be emphasizing is that the work done by friction is zero. Okay. The gravitational potential energy is decreasing because the object is coming down. Okay. And the kinetic energy is increasing. So when it's here, its kinetic energy is zero. Neither it has rotational kinetic energy nor it has translational kinetic energy to begin with. Okay. But by the time the sphere has come here, sphere, cylinder, whatever it was, cylinder, I think. Now it's got a linear or translational velocity and plus it's rotating. So it's got a kinetic energy which is equal to translational plus rotational. Okay. And at the same time, you can also see that the center of mass of that object has come down through a height h, which will be exactly equal to, now if you just draw this right angle triangle, you see the hypotenuse is L. This angle is the same theta. So this h is equal to L sine theta. Okay. So work done by external forces is zero. Work done by friction is zero because, I mean, you can say work done by non-conservative forces is zero because rolling friction does not do work. So if you take the cylinder plus the Earth's gravitational field as your system, then you can see that the change in kinetic energy plus change in gravitational potential energy should be zero. So the change in kinetic energy is basically the final kinetic energy. The initial kinetic energy was zero. So this is minus zero. And the change in potential energy is minus mgh because the center of mass is coming down through height h. So we have this relation that half m vcm square plus half I. Now I is how much for the cylinder? It is mr square by 2 into omega square is equal to mgh on the other side. Now since it is rolling, so that means that omega is equal to vcm by r. So we substitute that here. Yeah, okay. So this equation becomes half mv square plus half mr square by 2 into vcm by r whole square. That is equal to, and h is equal to L sine theta from above. So we have this relation. If you take half mv square common, we have 1 plus half. So we are having this value of vcm now, which will come out to be square root of 4 by 3 gl sine theta. So substitute those values. L was 20 meters and sine theta was 3 by 5.
Sir,
So
it
you get
is
this.
a lengthy method, no? But
Sorry?
sir, this is lengthy method, no?
This is the shorter method because see here you are first directly calculating it from one equation. No? There you are first calculating ACM, then applying kinematics. You understanding the point? So this is
Yes.
shorter, no, ultimately. So it becomes three cancels out, 5 goes 2 times. So yeah, it becomes square root of 160. The same value that we got here. So ultimately, see, you're just using one equation here. So that is the advantage in the work energy method. Just using the single equation. This equation, that's all. Whereas there you were first solving for acceleration, then you were substituting that acceleration in the kinematics equation, then substituting again in the constraint relation. So anyhow, with this we complete the chapter of rotational mechanics. Okay, you should at this stage look to complete HC Verma's rotational mechanics problems. at least in the next couple of days or before the weekend.
Sir, if you have doubt, you can ask in next class.
Yes, yes. I will keep some time for doubts also, and plus, if you have doubts directly in questions from HC Verma or module, you can just send me the question number or the picture of the question on WhatsApp. I will send you some hints also. But yes, we will keep some time for discussion of doubts once you complete these exercises before we come to the next part of the syllabus. Okay, so that's it for today's session, people. Thanks for attending. Wish you all the best.
Thank you, sir. Bye.